my grading sheet out of here. I got there, but all right. So chapter 10 and 11 together are about gases. Chapter 10 is the theory behind it. Chapter 11 is the laws that describe it. PV equals nRT. Okay. Okay, so we're going to start off with the why part first. And actually, speaking of that, before I forget to mention it, having graded these papers before in the past, I suspect that the most commonly missed questions I'm going to get are on 14, where it asks you to explain these things. Not to tell me what they were, but to explain them based on motion of molecules. Okay? That same question appears on your homework tonight. Okay? Same kind of question. Do not define the terms. Describe how molecules can make that happen. Okay? All right, so we're going to do the why part first. And the why for gases is called the kinetic theory. You may hear it called the kinetic molecular theory. But the key is kinetic. Kinetic that is from the root word for motion. So the theory is based on the motion of the particles. It says that molecules are in constant motion. Which molecules? All molecules, all atoms, everywhere are in constant motion. Since we're focusing on gases, a quick example of that is perfume. I open up a perfume bottle. Those molecules have to go across the room to reach your nose. Now, we're never going to see these molecules. Okay? But how do they know they're there? What kind of proof they have that there's little tiny particles all around us? Okay? I want to show you some advice, some evidence that talks about those. So, where's that?
This is what many people think of when someone mentions the word molecule. A collection of brightly colored balls stuck together in a particular way, with each ball standing for one action. It's better to think of molecules like this, as millions of tiny, fast-moving particles. It might seem a little strange to think of something as tall and solid as this bridge as being nothing more than a collection of fast-moving particles. But this is the way the atomic molecular theory looks at matter. We know that molecules are so small that even the largest ones are barely visible through the most powerful microscopes in the world. So we can't see the molecules in the bridge, but we can see indirect evidence that nearly everything around us is made up of tiny, fast-moving particles. And this machine will provide the first piece of evidence. Here is a piston that can slide up and down. Under the piston are some BBs. If we turn on this motor and touch the piston to this vibrating bit, the BBs are sent jumping. See how the continual bombardment by these very small BBs holds the piston up. If we put a weight on top of the piston, it goes down a little, but the bouncing BBs still hold it up. It certainly seems that a continual bombardment by smaller objects can hold up a much larger object. Here is a similar cylinder and piston, but this piston has no BBs under it. We'll blow air in under the piston, then close the valve so that none of the air can escape. Now, what's holding the piston up? The piston is being held up by air, but it acts just as the other piston acted when it was being bombarded by the BBs. Something we can't see is holding the piston up. It certainly seems that air is made up of tiny particles, far smaller than the BBs, and that these particles are bombarding the piston and holding it up. The name we use for these particles is molecules. Now, let's look at another piece of indirect evidence. The marbles here are a lot smaller and lighter than the sponge, but if there are enough of them, and if they're moving fast enough, they can push the sponge around. In other words, a lot of fast-moving small objects can push a large object around. Keep this in mind as we look at the next demonstration. With this device, we can capture smoke from a match in a chamber, and then examine the smoke with a microscope. The bright spots are smoke particles magnified 100 times. What's making them dance around? What's pushing them? This Brownian motion, as it is called, is caused by air molecules which push the larger smoke particles around, just as the marbles push the sponge.
So indirect evidence. We're never going to see it, so we have to go with indirect evidence. Yeah.
Don't they use pistons like those to determine someone's lung capacity if they're like pneumonia or something?
Yeah, actually the one with lung capacity is more of a flow meter that actually measures the total amount that comes out. The pistons, they use pistons like that in the shock absorbers in your car. Okay, because if you put springs in, springs bounce forever. The shock absorber will take that and be squeezed down and then be able to come right back up to where it was at without bouncing all over the place. So you have both springs and shock absorbers. The springs take up most of the force, but the shock absorbers keep the springs from doing this. Because I watched a car with no shock absorber on a rear tire on a freeway where their left rear wheel was occasionally on the ground. It was scary. So, what was the purpose of that video? What was I trying to prove by showing you that video? Nah. It's me. It's me. That's what I was trying to show you. Hey, I don't care what I need for a model of a smoke particle. Hey, I was trying to show you that I was showing you evidence of why we know the molecules are in motion. So, the kinetic theory. Okay, we're going to talk about gases. Okay. And in order to make the math easier, the kinetic theory makes 3 assumptions about the gas particles. We'll get rid of these assumptions later. Talk about what really happens. But to make the math easier, we're going to make some simplifying assumptions. First assumption, and my list is going to be a little bit shorter and different organized in the book, but all the pieces are going to be there. Book, I think, made it in 5 assumptions. Yeah. Okay. So how we talk about these particles? Okay. We don't care if they're molecules or atoms. Fact is, we want to treat them as just hard spheres. We're not worried about how they're going to chemically react. We're worried how they physically just move around. And we consider them far enough apart that we can ignore their volume. What does that mean? Well, if those molecules are far enough apart, they don't take up a big percentage of the space. Okay, imagine you're taking a bath and somebody drops a dozen bowling balls in the bathtub with you. Could you ignore the space the bowling balls took up? No. Okay, so you're in a hot tub and somebody drops a dozen bowling balls in. Could you ignore the space the bowling balls take up? A little bit better, but they're still going to be down around my toes, right? A pool. Olympic-sized pool. Somebody drops in 12 bowling balls. Are you going to notice it as much? No, because they're going to be further apart and take up a tinier percentage of the space. See, that's what we're talking about here. And actually, bowling balls in a Olympic-sized swimming pool is too close together. Ocean's too far. Yeah. And what's in between those molecules? Nothing. Well, but no, but in air, what's between those molecules? Nothing. And even in water, water is the molecules. What's between the molecules? Nothing. The molecules are the air. The molecules are the water. If you get rid of them, you don't have them. And if you don't have them, you've got nothing. And nothing has a name, we call it a vacuum. And the atoms themselves are mostly nothing to begin with. Okay, so this is how we're going to treat the molecules. We're going to treat them as little hard spheres bouncing around so small we can ignore their space. Because the math relies that the molecule can be anywhere in the container. Well, technically, it can't be in the same spot another molecule is in. So you'd have to subtract that away. We're ignoring that because it's going to be a tiny error because it takes up a little tiny part of the space. Okay. The particles are in constant random motion. And you don't have to make them random. What makes them random is they just move in a straight line until they hit another molecule, or they hit the wall and bounce off. The wall of the container, or off of the other molecules in there. Yeah, the wall of the container, yeah. They bounce off each other or off the walls. And a molecule moves on average a centimeter before it hits another molecule. That's how often they hit each other. Yeah, for how tiny they are. And actually, it's a lot for the other part of it, too. We'll talk about why it's a lot. And then all collisions are perfectly elastic. That should bring a question into your mind. Now, what's elastic? Because you're used to elastic as a noun. The stuff they put in sweatpants. Right? That's elastic. That's the noun. But here's elastic is an adjective describing a collision. And an elastic collision is one where when they hit, no energy is lost. That's the total amount of energy. That means they don't stick to each other at all. So an elastic collision is like pool balls hitting each other. Inelastic is like clay. They'll bounce off, but it'll deform along the way and absorb some of the energy. So they're saying that when they bounce, they don't lose energy. We know that's true because if they did, eventually they'd slow down and not move at all. And we wouldn't have things moving. So they're moving. How fast? How fast in this room? Well, in this room, the average oxygen atom is moving 1,656 kilometers an hour, which is 1,000 miles an hour. So the average molecule is moving 1,000 miles an hour. Ow, one just hit me. Oh no, they're hitting me all the time. I'm always being hit. Why do we feel them? The answer to that is two. There's two answers to that. A, we do feel them. And B, we don't feel the individual ones because they're too small. Even though they're going 1,000 miles an hour, we can't feel one of them. Okay. So now picture this. Picture this random motion. Okay. They're moving at 1,000 miles an hour, but every centimeter they change direction. No. That's that random motion. So if I open up the gas jet here in the front of the room, Andrew, can you smell the gas yet? How long would it take to get to you at 1,000 miles an hour? Okay, at 1,000 miles an hour, it wouldn't take any time at all, would it? But it is moving 1,000 miles an hour, but it doesn't get to move in a straight line. It's called a random walk is what it comes out to be, which just gradually spreads it out. Okay. So for 1,000 miles an hour, it takes them a long time to get anywhere. Okay. All right. What's temperature?
How fast the particle is.
If you look it up in the back of the book, I think your book says the degree of hotness or coldness. What a lousy definition. Okay, here's what temperature is tied to: kinetic energy, the energy of motion. And what temperature measures is it measures the average kinetic energy of the molecules, what the average is. So temperature is measuring the motion of particles. Now, because they're moving randomly, there's going to be a whole bunch of different speeds. So we can't talk about what every oxygen molecule is doing. We can only talk about what the average one is doing. So notice when I gave you the speed of the last one, I told you the average oxygen molecule, not what everyone. Because some are moving faster, some are moving slower. But in general, the higher the temperature, the faster the molecules. So by raising temperatures, you are making molecules move faster. Okay, let's think about the opposite. I lower the temperature. What happens? They go slower. And if I lower it more, it goes even slower. Is there a limit to how much I can slow it down? Nah. No, even in liquid and gas, liquid and solid, they're still moving. They never stop moving. Okay? Unless, as they get colder and colder and colder, they move less and less and less. We're not talking about them breaking, we're talking about stay together. Eventually, there would be a temperature where they would stop moving. And we call that temperature absolute zero. Yeah. Okay. At absolute zero, and that's a 0 Kelvin, capital K, that's where all motion would cease. And I put molecular motion, but it's not just molecular motion. All motion would cease. Okay, it's a theoretical limit, just like the asymptote on a hyperbola. Oh no, you can't say those words at any place but math. Okay, you never quite touch it, right? The asymptote. Well, the same thing with temperature. We can't quite get to zero, get lower and lower. The lowest temperature ever reached is on the order of 1/1,000,000th of a degree. Okay, and what happens when you cool things down that much? It's usually small groups of atoms, and when you cool them down, you're talking. What stops moving is the electrons stop circling the nucleus, and the electrons and the nucleus fall together into this big quantum soup called a quantum superfluid, where you can't distinguish between proton, neutron, and electron anymore. Okay? And then when you heat them up, the electrons pop back out. No. Suddenly I have an atom with electrons again. So the electrons disappear from the whole because the whole atom changes nature. No, not like the Ice Age. No, because Ice Age is, things are still moving. Okay. It's just a few glasses, and it would look like a little piece of, it look colorless because it's a gas when they're doing it. You can't let them bounce into each other because that would be motion. Okay, all right, so a temperature is not a number, a temperature is a curve. Okay, just like the curve that you get when you take the SAT, okay, that curve is, underneath the curve is everybody. You got a few people at each end with high scores and with low scores, lots of people in the middle. Okay, that's called a distribution graph. This is a distribution graph for temperature. Okay, a low temperature is where the blue's at. Lots of molecules with just a little bit of energy. As I heat it up, what happens is the area underneath the graph has to stay the same because that's all the molecules. So as I heat it up, what happens is it flattens out. And I get more molecules with high energy. So there's going to be very few molecules at the end with high energy, but as I increase the temperature, those numbers are going to go up. Okay? So what happens is the curve flattens out. So even at a high temperature, I still have some slow-moving molecules. I just have more of the fast-moving molecules. That make sense? So temperature is not what one doing, it's what the average is. In fact, here's where temperature is on these graphs. You'll notice it's slightly past the apex, slightly past the maximum. And that's because this right here, there's a zero. It really starts here. Everything stops right here. But this way, there is no end. They go on forever. So since I can get those way out there, they're going to weight more like a longer teeter-totter. They're going to weigh more over there, so it's slightly past. Okay? Slightly past half. It's slightly past the peak. But that's what temperature is. So when I'm raising the temperature, I'm flattening the graph. When I get to 1,000,000, the graph is almost a flat line all the way across. It's not that all the molecules are moving fast, it's that the distribution is flat. Okay. So average kinetic energy is directly proportional to the temperature in Kelvin. That means that temperature is measuring the motion of the particles. So if you double the temperature in Kelvin, you double the average kinetic energy. But it only works in Kelvin. So we need a way to get between Kelvin and Celsius. Remember we talked about temperature. There were two official units. Okay, so here's the official conversion. If I could get a pen that writes on this thing. Celsius, add 273, you get Kelvin. Because it's degrees Celsius. It's not degrees Kelvin. Kelvin doesn't get a degree sign. That's where it goes. Degrees Fahrenheit? Yeah, that's where it goes. The degree goes before the C. Like 25 degrees Celsius. 25 degrees Celsius. Okay, so what does that degree sign mean? It looks like a zero, right? Right? Because that's what it means. It means zero. It means somebody picked zero. Celsius picked the freezing point of water to be zero. He picked it. Kelvin, did they pick zero for Kelvin? No, there's really a zero. So Kelvin doesn't get a degree sign because it wasn't a matter of picking. There really is a zero. They really started at zero. They didn't pick some arbitrary place. So you think about your protractor, you pick where to lay it down. You pick which angle is zero. That's why it's got a degree sign, because you get to pick zero. Hadn't thought about it that way. Okay? Hey, tonight's homework is going to ask you to convert Celsius and Kelvin temperatures. Okay, I'm not going to do a lot of examples. I think you can handle that one, right? Okay, the secret to that, though, is remember, Kelvin's always bigger. So when you're done, is your Kelvin answer bigger than the Celsius? As long as you got a bigger Kelvin, you went the right direction. So pressure. Pressure is those collisions. We do feel those collisions. You feel the difference in those collisions when you go up in the mountains. Because the air inside your head has a different number of collisions than the air outside your head, because there's fewer molecules up high. So fewer molecules hitting your ear, so the eardrum bows out, so you want it to pop, so you swallow, which opens up little tubes at the back of your ear canal called the eustachian tubes, so the molecules can go in and out and equalize the pressure. If you got it cold and those are blocked, you can't equalize the pressure, and an airplane can get bad enough that it pops your eardrum. at least you're going to have a very miserable flight. Ask my sister. Okay. A vacuum is completely empty space. It has no pressure. And because I spelled it wrong till I was about 25, vacuum is spelled correctly here. 1 C, 2 U's. Yeah, that's the right way to spell vacuum. It's the only word I know of with a double U in it. Yeah, I did 2 C's instead of yeah. Because I couldn't believe it was 2 U's, but it really is 2 U's. Okay, unit of pressure is the atmosphere. And we talked about that when we talked about STP, standard temperature in Kelvin, and pressure. Pressure, we said, was 1 atmosphere. It's abbreviated ATM. Okay. So, here's how they first measured pressure with a device called a barometer. Okay, we don't use these kind of barometers. We come to different ones now, and here's why we don't use them. Okay, to build this kind, you start off with a long glass test tube, and you fill it to the top with mercury. And then you put your finger on the top of it. Flip it over, and put the opened end into a dish full of mercury. It's the mercury is the reason why we don't do this anymore. Mercury causes Dame damage and birth defects. Okay? So, when you do that, just like when you put your finger over the straw at Carl's, everything stays in, the mercury will stay up the tube, and if there's 1 atmosphere of pressure, that column of mercury will be 760 millimeters high. Why does it go up the tube? Well, what's at the top of the tube? Well, it was full of mercury, then the mercury fell down, so what's left here is nothing. That's a vacuum. Out here, we got lots of molecules bouncing off the surface of that mercury. So the mercury wants to go someplace where it won't get hit. Where does it go? Where it doesn't get hit? Up the tube. And the more it gets hit, the further up the tube it goes. So the taller the column of mercury. When you listen to the weatherman, they talk about the barometric pressure is 30.08 and rising. What they're talking about, well, here's 760 millimeters, right here. The other side, that's right about 30 inches. They're talking about inches of mercury instead of millimeters. So they're talking about the same kind of barometer. Hey, I can write 1 atmosphere is 760 millimeters of mercury. And guess what I can make with that? Conversion factors. The 760 is the definition. They decided to define 1 atmosphere as what 760 would be. Eliminating sig figs on that one. Since the guy who invented that barometer, his name was Torricelli. They wanted to name the unit after him, but nobody wanted to write out Torricelli. So they shortened it to Tor. I don't know why. It should be capitalized according to me because it's somebody's name, but the official unit is the Pascal. Okay? But Pascals are really tiny. It takes a lot of them to equal an atmosphere. It takes 101,300 pascals. And nobody wants to write 101,300. So instead they write 101.3 kilopascals. Okay, and it is the same. It is the same Pascal, Blaise Pascal for Pascal's triangle. He was not just doing math; he was doing science, kind of like Newton. Okay, so tonight's homework is going to have you do conversion factors with these. Do I need to work out lots of examples? Okay, if you want some examples, they're in the book. Just remember the 760 is unlimited sig figs. Okay, that's the only mistake you could really make here. Okay. So, temperature measures how fast they're moving. Pressure measures how hard they're hitting. Okay? That's what temperature and pressure are. Okay? Now that we can talk about temperature and pressure, we'll use that to explain the world around us. Okay? Is that right? Makes sense? But there'd still be